We're going to review how to work with complex numbers, specifically in what they might call standard notation, or I call complex notation, and then turn it into trig form, or trig notation. So first off, a complex number. This is a complex number. It's kind of a number written as a plus b I. It's got a real part and then the imaginary part. Together they make a complex number. If you remember, this question doesn't have us do it, but what we do is we can actually graph a complex number. Let's see, let me write on the right side. We can graph a number in what we call the complex plane. We actually have the real part that we graph over here and the imaginary part we graph in the vertical direction. So the real part is the horizontal axis, formerly known as the x-axis. And then now the imaginary part is the y-axis or vertical axis, formerly known as the y-axis. So for this problem, you could think of it as the point negative 3 root 2, that's the real part here, comma, negative 3 root 2 for the imaginary part. Notice we don't carry over the imaginary part, we just note the I, it makes it the imaginary part. So actually this would be the coordinates. And if I were to graph this, I would actually just graph it to the left, negative 3 root 2, whatever the heck that is. And then it would go up. Actually, no, I'm sorry. It's negative in the imaginary or vertical direction, so it'd go down. So it's actually like a point right here. So notice we actually went to the left, negative 3 root 2. And then we went vertically down, also negative 3 root 2. So there's the point along what we used to be the x and the y-axis, but now it's the real and the imaginary axis. Well, we're actually going to turn it into some weird trig notation form. And it's going to have the same kind of a plus bi form, but it's not going to be like x's and y's or a's and b's. It's going to be more like r's and thetas, kind of like polar form, like trig stuff. And so there's actually a formula for it, and let me just go right to the formula. The formula, the trig version of this a plus bi, is actually, I'll write it two ways. First, I'll write it r cosine of theta plus r sine of theta, and then I. In fact, you know what? I should wrap that in parentheses there because the I is not in the angle in the trig function. But we actually, since both parts have an r, we usually factor the r out. So it actually looks a little bit more mysterious, and it's like this. And then again, because of that i's there, I either need to wrap this in parentheses, or what I could do is actually bump the I in front. So it could even look like this. Cosine of theta plus I sine of theta. Then I don't have to wrap that parentheses to emphasize that the I, the imaginary number, is not in with the angle for the sine. Okay, so if I'm just going to turn it into this formula, I actually need to know, oh, how do I turn the a's and b's into the r's and thetas? Well, I mean, there's a formula for that, and I'll show you the formula. It's actually just r is equal to the square root of the a square plus the b square. And let me show you where that comes from, because instead of memorizing formulas, just this picture says it all. The r is actually the radius, that distance out, which you can also call the absolute value of the complex number. It's the distance from the origin, 0, 0. So really, it's just the hypotenuse. So really, it's just a squared plus b squared equals c squared. Technically, it's r squared equals negative 3 root 2 square plus the b square. Actually, there's the a square. Here's the b square. Negative 3 root 2. Well, there's the b, which we got to square. All right, and of course, the reason why the formula looks like this is because then we just got to square root all this and square root the whole shebang over here. Remember, you can't square root individual pieces when there's addition there. And that's what we're going to do to get the radius. So really, the radius is going to equal the square root of this square. And what is that? Well, of course, negative 3 times negative 3 is positive 9. But then root 2 times root 2 is normal 2. So let me just kind of show this, that it's actually a positive, because negative times negative is positive. There's going to be a 9 in there, because 3 times 3 is 9. But we're also multiplied with a root 2 times a root 2, which is normal 2. And so it's actually 9 times 2. In fact, same thing right here. It's the same thing. So it's actually just a positive 9 times a 2, which actually means it's really just, get my pen back. It's really just the square root of 18 plus 18 Actually, 18 and 18, isn't that just 36? This is the square root of 36, which, wait, isn't that just 6? So our radius must be 6. R must be 6. Okay, so that's going to go in my formula here to turn it into the trig notation, or kind of like a polar notation type of thing. It's going to be 6 times, and then now we need the angle. So we can do cosine of some mystery angle plus the imaginary number times sine of some mystery angle. So we just got to figure out that angle. Well, what angle? Well, we could think of it as the angle in this triangle, but technically it's the angle that gets us into this quadrant. So let's make sure that when we get this angle, we get the correct angle to put us into quadrant 3. Well, how do we do that? Well, again, there's a formula for it, and I'll write the formula, but then we'll look at the picture. The picture will tell us the formula. So the formula is the angle is going to equal the tangent inverse of B over A. That's just because in this picture, if I want the angle here, it's just opposite over adjacent is the tangent, and we want the tangent inverse for this. So if I use my formula, or if I just use the triangle, I go opposite over adjacent for tangent, and then tangent inverse. So it's actually just going to be the tangent inverse of negative 3 root 2 over negative 3 root 2. And of course, negative over negative, I don't even need those. In fact, wait, 3 over 3, root 2 over root 2, wait, this is actually just the tangent inverse of 1, a giant 1. And if you have that memorized, great, you should. But if I just fire up Desmos, just in case, maybe I don't have it memorized, if I just pull up the tangent inverse, and I do the tangent inverse of 1. Oh yeah, 45 degrees, because I'm still set into degrees. I should double check. Always check, yep, it's degrees. Yeah, that makes sense, that angle is just 45 degrees. So that angle is perfectly 45 degrees, and it should make sense by looking at the picture. Remember, of course, I circled it, but that's not really my answer. But this should make sense that, yeah, this is a 45-degree triangle. This is isosceles triangle. It's like 1, 1, square root 2. It's just been amplified bigger. So yeah, it's 45 degrees. But wait a minute, actually, hold on. 45 degrees. If I were to draw 45 degrees down over here in this corner, that would make me draw the triangle in quadrant 1. That's because tangent inverse of a positive puts you in quadrant 1. All students take calculus. We keep this quadrant for the tangent inverse when we do it on a calculator and not this quadrant. But sadly, that's the quadrant we want. We just need to manually bump it over there. So it's actually a 45-degree triangle. This is a 45-degree angle, but it's in quadrant 3. So we got to bump it over by adding the 180 degrees. So it's actually not 45. We got to bump it by 180, which would make our real angle, what, 225. So that's what's going to go over here in our formula. 225. 225 degrees and 225 degrees. So this is my trigonometric form or trigonometric notation, also could be called like polar notation for my complex number. Here's the normal complex number version. Here's this alternate version for an alternate universe. All right, let's try another one. In fact, this is the same kind of thing. For the sake of time, let's just jump right using the formula, okay? So this is A plus BI. A is the negative 10 root 3, and B is 10. We need to turn it into this other form, like R cosine of theta plus sine of theta. Oh, but this part has the imaginary. I'll put the imaginary in front. There we go. Now, earlier I didn't really explain why it was cosine theta and then sine theta. So, yeah, oh well. We can go back and do that later some other time. Again, for this one, let's just go straight to the formulas. We need the r and the theta. We knew that r was actually just the square root of a squared plus b squared. It's just Pythagorean theorem from our triangle. We're going to square that, and we're going to square that, and we got to square root the whole thing. So let's just quickly crunch that. All right, 10 squared is easy. That's just 100. But this one, well, negative times negative is positive. 10 times 10 is 100. And then root 3 times root 3 is actually normal 3. So we got to multiply by that. Because this is multiply. Bloop, so we got to multiply. All right, so our r is really the square root of 300. And it's plus the 100. So it's actually the square root of 400. And let's see, I know the square root of 4. I'm just kind of doing mental math here. That's 2. I know the square root of 100. That's 10. So doesn't it make sense that this would just be 20? 20 times 20 is 400. So there's our radius. We know the radius is 20. 20 times, and then we just need the angle because we're going to do the cosine of the angle plus the imaginary part with the sine of the angle. So let's find the angle. And if you remember, the angle is actually the tangent inverse of the b over a. It's the vertical component over the horizontal component. It's the opposite over adjacent, okay? And so it's b over a. All right, so let me zoom out a little bit here. So if we actually plug that in, plug in the numbers, it's the tangent inverse of, what's the, b is 10, over a, which is negative 10 root 3. Remember, b is here, the imaginary part, and a is here, the real part. Whoa, 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 why is it stuck? Oh, jeez. Let's get rid of that. Oh, it's like not even, doesn't even recognize that as being there. Well, it's freaked out. Will it erase it? It's not even undoing it. Oh, well. Let's just ignore that craziness that my computer just did. Okay, so actually, 10 on top cancels 10 on bottom. And let's see, oh, it didn't write the root 3, or it erased it. So let's rewrite this because I got that crazy squiggle on the screen. So it's going to be the tangent inverse of 1 over, because I canceled the 10s out, negative root 3. In fact, you know what? I like to move the negative on top or even out front. It's negative 1 over root 3. Okay, so I could go into Desmos. In fact, you know, I will, just in case I don't recognize that. Let's just use the formula. Let's see what we got. Okay, tangent inverse of, this is from my last problem. Let me just change this to 1 over, actually it should be negative 1 over the square root of 3. Negative 30 degrees? Okay, yes. So it's 30 degrees, but it's negative. Okay, so let's double check this. Let's draw our picture. This should actually be what kind of graph on the real and imaginary plane. So the real part is the negative 10 root 3, which is this way. So I'm going to, in fact, let's just mark that. We're going to go whoop, negative 10 square root 3. And then in the complex part, or I should say the imaginary part, in the imaginary direction for this complex number, it's going to go up or vertically 10. And of course, I didn't really draw it to scale. So that's actually a right angle. Of course, we already found the radius, r, that's 20. Just a squared plus b squared equals c squared. And now we just found the angle, but hold on. It said the angle was, wasn't it negative 30? That would be in quadrant 4 as a negative 30 degree triangle. But we actually want still a 30 degree triangle. In fact, maybe you recognize this as being a 30 degree. This is a 1, 2, square root 3. It's 10, 20, 10 root 3. This is just 10 times bigger from our normal 1, 2, square root 3 triangle, which is 30 degrees right here. But we can't say the answer is negative 30, or it would be in quadrant 4 point, but that's not what we have. So we actually have to bump it to here. So what would that be if it's 30 degrees here? That would be a 150 degree angle. So that's my real true angle. Okay, so there we go. Now notice the triangle is almost better than just memorizing these formulas and using it. We kind of need the triangle anyways. In fact, the triangle also helps us realize this formula here is why in the heck is it cosine of theta here and then sine of theta for the imaginary part? Well, that's because the real part is this horizontal or adjacent part. And of course, that's a cosine problem, especially when you're dealing with the radius as well. So it's adjacent over hypotenuse, which is the radius. And of course, the imaginary part is the vertical component. And you know, it used to be a 10 there in the vertical imaginary component, but now it's going to be this piece of our triangle situation, which is, you know, the opposite, especially when dealing with an angle and the radius. It's opposite over hypotenuse, or the opposite over the radius. So we did get a chance to talk about why is this the cosine of theta and this is the sine of theta. So really, we're done. We have our trig notation, or like polar notation, using r's and thetas for this original complex number. Okay, let's go to another one. Hopefully my pen doesn't freak out again. Now actually, check this out. This one gave us the trig form. This must be the r. The way they've written it, this is the r. And then notice they bumped the I in front like I did. They put the cosine of theta, that's our theta, plus the imaginary part has the sine of the same theta. Oh, you know what? I'm going to write theta there. In fact, let's fix that sine. So there's theta as well. So we already know that r is root 8, and we already know that theta is pi over 4. Oh, you know what? I just realized since that's pi over 4, did they tell us to put the angle in radians? Yeah, my pen scribbled all over it. We were supposed to put that angle in radians. Let's quickly fix that now that I noticed it. Okay, we were 30 degrees, which 30 degrees is what? Pi over 6. 30 degrees is pi over 6. And we were 30 degrees shy from a full 180 to get our 150. And so a full 180 is a full pi. That would be 6/6 of pi. But if we take away this 1/6, then this angle is actually 5 pi over 6, or 5/6. So we should really rewrite this with a 5. That's looking a little sloppy. With 5 pi over 6 as our angle. Same thing here, 5 pi over 6 as our angle in there. All right, well, let's go back to this one. This one is in radians. All right, where were we at? We got our radius, we got our angle, they gave it to us. Ah, yes, we need to turn this into the good old normal, a plus bi. Well, actually, if you look at this, if I just distribute r into this, boop, bloop, it would be r cosine of theta plus boop, bloop, r sine of theta with the imaginary thing. So actually, if I color code this, this is our real part, and this is our imaginary part. So we have a plus bi. So there's actually the formula. Our a is going to be r times cosine of theta, and the b is going to be r times sine of theta. So really, we just plug it in and crunch it. So a is going to be root 8 times the cosine of pi over 4. And then b is going to be root 8 times the sine of pi over 4. So we just need to crunch that. Now, okay, how do we crunch that? We could use a calculator and Desmos, but we probably want to see if we can get exact value, because this angle is pretty nice. Pi over 4, that's just a 45-degree triangle. That's quadrant 1. That's just 45 degrees. So this is like a 1 square root 2. Okay? So a is actually just going to be root 8 times, well, what is it? This is adjacent over hypotenuse, so 1 over root 2. Okay, let's crunch that. So, wait, just make that a fraction. Top times top. Bottom times bottom. Of course, root 8 over root 2 is actually just root 4. You can divide roots. Roots are all about multiply and divide. So this is just root 4, which is just normal 2. So a is 2. We need that for our answer. And let's do the same thing for b. Oh, wait a minute. b is actually just square root of 8 times the sine of pi over 4. And that's just opposite over hypotenuse, but that's a whole lot like adjacent over hypotenuse. Right? We've kind of already done this. I can make that. I can put it as root 8 over root 2. That's an equal sign, which is just really just root 4, which is really just 2. Oh yeah, 45 degrees, the vertical and the horizontal component are exactly the same. Notice this is 45 degrees, that's in quadrant 1. So these are actually both positive, positive horizontal direction, positive vertical direction. So I think I got it. My complex form, or they call it standard notation, my complex form is actually 2 plus 2i. Easy peasy. Notice I still drew a triangle for that one. All right, we got one more. Find the standard notation for this. Same thing. This would be like 6 if I distribute. Boop, bloop. 6 times the cosine of 120 plus boop, bloop. 6 times the sine of 120. Of course, with the imaginary number. I'll put it over there. Of course, I guess that means I should put parentheses there. Let's be consistent. And so there we go. We actually have the A plus the B I. Well, it actually just shows me what I need to do for A. A is just going to be this guy. And then B, if I change colors, B will be just this guy. And then it will look right. So let's crunch it. 120 degrees. Let's draw that triangle over here. 120 degrees. Actually leaves us in quadrant 2. Of course, how much angle is left to make a full 180? That would be 60 degrees. This is, famous triangle as well. This is a 1, 2, square root of 3. Notice 60 degrees is the bigger angle from the 30, so this is the 1. Okay, oh, wait a minute. It's quadrant 2, so this is negative in the horizontal component. So that means my value here should come out negative. Yeah, 6 times the cosine of this picture. What's cosine? Cosine is adjacent over hypotenuse. See, it's using the horizontal component. And then a 6 times negative a half, that's just negative 3. Plus, let's do the vertical component, the imaginary part of this. That would be 6 times opposite over hypotenuse. And notice this one's positive. That's because it's going vertically or up. And there we go. And of course, wait, what is that? This cancels, and it's just 3 square root of 3. Of course, don't forget this is the imaginary part. We need the I there. Okay, so here's my A plus BI. The problem here is that square root. I don't like anything really after the square root. This I does not belong under the square root, and sometimes when you write it after the square root, it like accidentally slips underneath, and we don't want to do that. So what I'm actually going to do is I'm going to rewrite it, but I'm going to bump this guy in here. Not in front of the nice 3, but in between the 3 and the square root of 3. So we often write it like this, 3 plus 3i square root of 3. And that is my complex form, or they call it standard notation of this complex number.